Um, so this is sort of the next big thing that we see with the use for capacitors. Really, the primary use for capacitors is to store energy. I think you might even have a question on your test like that. But the primary purpose for capacitors is to store energy. But we'll see with RC circuits that you can create a circuit that will actually change with time in a very predictable way. And that can be useful if you want to have something that repeats over and over and over again, like flashers on your car. Those use capacitor circuits to have the flash go off and on and off and on. Anytime you want to have something repeat with a very regular way, it's usually because it's using a capacitor. And it still stores energy, like it's storing energy and then it's using it. Storing energy and then it's using it. Storing and then using. And so, next time you're in your car and you put on your flasher, if y'all use your turn signals, I'm not sure that you do, any of you. But next time that you're in your car, think, oh gosh, tell your friend next to you, it's a capacitor. All right, so we'll see that with RC circuits. We're also going to see exponential functions, which is very important for you biologists. If you haven't seen them yet, I'm sure you've seen them somewhere, but just to get some practice with exponential functions, because often you have things that respond in an exponential way, right? As, I don't know, populations, or I don't know what y'all do, but you have things that respond in terms of an exponent, or an exponential. Okay, so in circuits with capacitors, the current varies with time. Oh, I lost my pen. Give me just a second. It's usually fixed. We're back. So in circuits with capacitors, the current varies with time. After the circuit is turned on, if I have a circuit like this, when I turn on this switch, when I flip it closed, I send a current through this resistor where it goes until it fills up this side of the capacitor. So remember, this capacitor stores a certain amount of charge. Now when I turn on this circuit, that charge flows through this resistor and goes and deposits itself onto this plate of the capacitor. And it does that until the capacitor is full. Now when the capacitor is full, the capacitor says, whoa, no more current. I can't take any more charge, and so it will stay with a steady state. Now when that capacitor is fully charged, the charge is equal to Q equals CV. We've seen that. That's like the maximum charge that you can have on that capacitor. But as it's charging, the charge is given by this exponential function. So these are in your equation sheet, but you need to practice with these. There's some homework. You're going to see some exponentials on your test. Just make sure that you know how to deal with exponentials. So as it's charging, it looks like this. It's the total charge. That's the same as this value, by the way, times 1 minus e to the minus t divided by RC. So similarly, if I wanted to plot the current, so this is the charge on the capacitor, and the function for the charge on the capacitor looks like this. It approaches a certain value. That value that it's approaching is equal to Q. So when t gets really, really big, this term is e to the minus a really, really big number. This term goes to 0, and so my charge just approaches this value. As time goes on, my charge reaches the total charge, which is Q. The current, on the other hand, is going to look like this. It's V over R. That's your maximum current. This current occurs when there's 0 charge on the capacitor. That current occurs right here. It is our maximum current times e to the minus t over RC. All right, so what we see here is a growth exponential because it's increasing, and then a decay exponential because it's decreasing. You might not ever see capacitor RC circuits again. In fact, probably you're not ever going to see them again, but you'll certainly see exponential functions if you haven't yet in your studies biology. Probably you may or may not see capacitor circuits. Sometimes they talk about them in terms of the electric properties of the cell, but usually not. So after you charge a capacitor, you can take away the battery, usually using a switch or something, or if you want to physically take away the battery, then what you have is you have a capacitor that's all charged up, and then you have a resistor. You can close the switch. Goodness. You can send that charge through the resistor, and you can discharge that capacitor. And these all decrease with time in these decay exponentials. They look like this. Q is equal to Q times e to the minus t over RC. I is equal to V over R times e to the minus t over RC. And then the voltage is the initial voltage times e to the minus t over RC. This initial voltage is equal to Q over C, or you can think of it as the voltage of the battery. All right, the battery is what puts those charges on that capacitor, so the capacitor has this voltage, which is equal to the voltage of the battery. But it decays with time. So after you close the switch, you start out with some maximum value of the current, the voltage of the charge, and it decays with time. You need to know what those plots look like for the decay or the growth of either the charge or the current or the voltage for a charging or a discharging capacitor, and we'll do some practice. And then you also need to know how to calculate the charge or the voltage or the current at a particular time, how to solve that function for time. Let's see, I think we'll have an example, but let me just sort of go through one. Let's say that I have this and I want to solve it for t. Y'all know how to solve that for t? What function are you going to use to get rid of the exponential? Right, you use the logarithm, the natural logarithm. So let's say I want to just solve this function for t. Q is e to the minus t over RC. I would divide both sides, first of all, by big Q. And then I get Q over Q equals e to the minus t over RC. And then to get rid of that exponential, I do the natural log of both sides. And then that gives me the value for t over RC. So I get the natural log of Q over Q. It's a function on your calculator. Is equal to negative t over RC. And then from there you can solve for t. T would equal to R negative RC times the natural log of Q over Q. So there's some homework where you have to solve for these various things, but you do need to be able to solve for any of these quantities in these various decay and growth functions. Okay, I think we have an example in just a bit where we'll solve for one, but also look in the homework and look at the old test, because you'll certainly have a question like that where I ask you to solve for what is the charge at this particular time, or when the charge is this, what is the particular time? Solving for t, solving for q, solving for any of those variables. The time for charging or discharging a capacitor is characterized by something we call the time constant. The time constant of this Greek letter tau, and it's equal to the resistance times the capacitance of the circuit. The units for the time constant, it's a time, so it's equal to seconds. If you look back at these functions, I can rewrite them. I'll come back to this, but I can rewrite, say I want to take this, I can rewrite it in terms of the time constant. I would say V equals V naught times e to the minus t over tau. So it's not just for RC circuits, but often in exponential decay or growth, we use a time constant to characterize how long this decay curve takes to fully decay, or how long this growth curve takes to fully grow to its maximum value. And we use this thing called the time constant. Now the time constant isn't the time that it takes to fully decay or grow. It's actually 10 times the time constant. So after 10 tau, the capacitor is basically fully charged or fully discharged. That is, if I was to plot Q over T, or Q versus T, is this charging or discharging, this capacitor, if I plot it like that? This is a charging capacitor, right? It has 0 charge at first, and then it grows to some maximum value. This is that 1 minus e to the minus t over RC. This is a growth curve. And so what this is saying is that after 10 tau, basically out here, after 10 times that time constant, that's when we say this capacitor is fully charged. Now, the capacitor never actually gets fully charged, right? In an exponential growth curve, it never actually reaches the maximum value, but we say that it approaches that value, that it gets very, very, very close. 99.99%. But it will never actually reach the maximum value. That's how these exponential curves work. All right. Let's try this one. I want you to notice, you need to calculate the time constant here. And I want you to notice that when you calculate the time constant, that you'll need to look at your units. I have a megohm here and a microfarad here. Remember, mega is 10 to the 6th, and micro is 10 to the minus 6th. So often I'll use those just because it makes your life a little easier. You restart my business here. All right, if you have your answer, you can go ahead and put it in. Feel free to ask your neighbor if they put it. All right, let's do about 12 more seconds. Stop at 1 minute. Just guess if you're not sure. Many of you have the right answer. Maybe about 10 of you don't. I'm going to stop at 105. 105. Okay, good. A is the right answer. It seems more complicated than it is, really. You want to solve first, find the time constant. Tau is equal to RC. That's 1 megohm times 4 microfarads. I can write these out. That's 1 times 10 to the 6 ohms, 4 times 10 to the minus 6 farads. I want to convert those to SI units. But usually when you see problems like this, I'll use the meg micro combination because it just gets rid of that. And then my time constant is 4 seconds. But the answer is not 4 seconds because to completely discharge this requires 10 times the time constant, which is going to be 40 seconds. The time constant isn't the time to fully charge or discharge on your growth function or your decay function. It's a 1/10 of that time. And we just sort of use that to characterize it because it's in that exponential function mainly. All right, you go down from here. All right, what is the resistance, or excuse me, what is the capacitance of this capacitor? The time constant is 1 second, and the resistance is 1 megohm. What is the capacitance? I see all the units here should be farads. I just noticed how it coulombs here. But all the units should be farads, microfarads. Oh no, I take that back. This one is supposed to be coulombs, and this one's supposed to be farads. Sorry. All right, let's stop at 130. 130. Okay, good. C is right. So I say tau is equal to RC. That's my time constant. Time constant is 1 second. Resistance is 10 mega ohms. What is my capacitance? If I solve for that, it's 1 over 10 times 10 to the minus 6, which is 0.1. Is that right? Yeah, 0.1 times 10 to the minus 6. Yeah, not minus 6. This would be positive 6 right here. Sorry. So the answer is 0.1 microfarads. All right? Know how to calculate the time constant and know what it means in terms of discharging or charging a capacitor. It's sort of related to, actually. I don't know if y'all knew this, but there is a long lineage of electric detectors. Did you know that? Do you know who the first electric detector was? Sherlock Holmes. Y'all thought I was serious, didn't you? For just a moment. Yeah. All right. Let's look at household circuits. So, just sort of rewind. Know how to calculate the time constant, but you also need to be able to calculate the time or the charge at any particular time. Look at the homework. There are some good examples there, and then also look at the old test. Be able to calculate Q given the growth or decay function, and then also be able to calculate any one of those other variables. Let's look at household circuits. You'll need to know sort of the basic setup of your house, how it's set up, and then also some of the safety features in your home, including the circuit breaker, the GFCI or the GFI, the grounding in your home. You'll need to know those safety features, what they do, but you also just need to know how the house is set up, how your house is set up. So you have 3 wires that come into your house. You have this transformer outside your home. All right, here's your house. You have your pole outside. It's like this. You have a transformer. It's basically a big can of oil, big can of mineral oil that has these 2 metal coils inside of it. We might watch a video later where they show how they make it, but it's not entirely relevant for us. But you have 3 wires that come off of this. All right. Of those 3 wires, you have one that comes in at plus 120 volts. You have another that comes in at minus 120 volts. And then the third is a neutral wire or a ground wire. All right, so you could go up and touch that third wire and it wouldn't bother you. But the other 2 are plus 120 and minus 120. So, you know, most of your house operates at 120 volts, right? You know what? Some of your house operates at other voltages. Do you know what those are? No, not 60. 60 is actually the frequency. We're not going to get into AC electricity, but you actually use alternating current. We've been talking about direct current, and 60 refers to the frequency of how often that current changes phase. The other, we have devices that operate at 120, or sometimes you say 110 volts. The other devices operate at 240 volts. And 240 volts will connect this wire and this wire because the potential difference between 120 and negative 120 is 240. So what type of devices in your home operate at your oven, if you have an electric oven, your dryer, not your washer. Your washer usually operates at 120. It's just a simple motor. And then if you have electric heat, that operates at 220. You know how the plugs are different? Okay, they all have crowns, but like if you have one plug that you stick in the wall, we don't have electricity in this room. But if you have in this building, you don't know that. These are all oil lamps up here. Very old building. Tell the president that they need to remodel this building. Anyway, what was I saying?
Something about plugs.
Oh yeah, so think about those plugs. If you've ever seen them, most of your outlets in your home have 3 holes, right, in the plug. But if you look at your dryer plug or your oven plug, they have to have 4 holes. That's because you've got this extra minus 120. All right, we'll talk about that in just a moment. So these wires include 2 hot wires. That's the plus and the minus 120 volts, and a neutral wire. So these wires, they come into your home, got those 2 plus 120, minus 120, and then there's the neutral, and they come in from that transformer like that. They go through your meter. The power company uses this to tell how much energy you use in a month. So it gauges all the electricity that goes into your home, and they go to a circuit breaker. And often you have lots of different switches, and we'll talk about circuit breakers and how these work. But from your circuit breaker, it breaks into a bunch of parallel circuits. So you might have 10, 15, or maybe if you have if you're really rich or something, you might have like 20 circuits in your home. No, we don't have 20 circuits, we have like 10. But you have all these different circuits in your home that operate in different things. So like your lights in your bedroom and maybe the bathroom might be on one circuit. Certain portions of your house, the lights are them. Or the electrical outlets in certain rooms might be on a circuit. But they're all laid out in parallel. So for example, if you have one circuit, of which you have many in your home, you would have your 120 volts, and here you would have your bedroom light. Here you'd have, say, your radio, or your boom box, as they say, and then here you'd have, I don't know, your fan, I don't know, whatever's on that circuit. But they're all laid out in parallel. Now that's important because that makes a couple things true. What is it about devices in parallel? What do we know about resistors in parallel? They all have the same voltage. And that's one of the main reasons all devices will operate at the same voltage. Listen, you don't want to have your house laid out in series. Because if it was laid out in series, if you had one thing turned on, then the voltage that was available for the other thing would be different. But you can never really design an electrical device because you would never know what voltage you would have for your device, right? Because it would depend upon what else was on the circuit. But with this case, it doesn't matter if your fan is off or on. Your radio is always going to get 120 volts. Another thing that is the result of this, and this was actually sort of the junction rule. Remember the junction rule? That in a parallel circuit, the current going into a junction is equal to the sum of the individual currents. And so the result of that is that on a circuit in your house, one of those many circuits that you have in your house, if you increase the number of devices, you increase the total current. That is to say that, going back to this circuit that we have up here, that I have a total current right here. And that total current is equal to the current here, plus the current here, plus the current here. That I total is equal to I1 plus I2 plus I3. That's true for resistors in parallel. And if that's true, what that means is that as you add more and more devices in your circuit, you get more and more current. Now the wires in your home, they can only hold so much current, right? Those the wires that run in your walls, they can only operate at say 15 or 20 or maybe 30 amps. But if you exceed that current, then they can, well, they can catch on fire. They can melt or break down. And so we have several safety features to prevent that, and some other maladies. The first is the circuit breaker, which you're probably familiar with. Or you might have a fuse box. We sort of have a hybrid circuit fuse box in our home, but it's pretty old. The next is the grounding of your home. If your home is, I don't know, less than 50 years old, then it's grounded. And the GFCI, the ground fault circuit interrupt. I'll write that out for you later. Let's look at the circuit breaker first. What the circuit breaker does is that it turns off the circuit if you exceed a certain amount of current. Y'all all done this, right? You turn on your bathroom heater and your microwave on the same circuit, and it kicks off, because both of those things, they pull a lot of current. And so if they pull too much current, your circuit breaker will turn off. It keeps those wires from burning up. It doesn't mean that you damaged anything. It just means that you had too much on that circuit for a brief moment. So a circuit breaker or a fuse looks like this. Some of you might have fuses. You don't need to write this down, but I'm just sort of, it has like a little glass window with a metal tab inside of it. If you look at it from the side, it sort of looks like a light bulb, but without the bulb. Y'all seen fuses before? You screw them into it, you have a fuse box instead of a circuit breaker. Like, so we have fuses and circuit breakers. Some fuses look like shotgun shells, but they're not shotgun shells. But these work so that the current flows through this metal tab right here, and if you put too much current, it just burns up that tab, and then you pull it out and you throw it away and you put in a new one. So a circuit breaker or a fuse turns the circuit off if the current exceeds the safe capacity of the circuit. You can tell if you look on your circuit breaker, usually on these switches right here, there'll be a number. It'll say 15 amps or 20 amps, or maybe you have a 30 amp circuit. That means that the wires in your wall are rated to handle 15 or 20 or 30 amps, as well as the actual breaker itself. So most will turn off if the current I total is more than 15 or 20 amps. Circuit breaker panel there. Many of you have a main breaker as well. What this does is this takes you off of the grid. So you're not really supposed to do this, but I know that people do this around here. Is that you take a generator when you're out of electricity? What do y'all do? Right, you take like an electrical cord and you strip off one end and put 2 nail ends on either end. Y'all done this before? You plug one end into your generator and then one end into an outlet in your wall, and that charges that circuit. Y'all follow what I'm saying? You're not supposed to do that. Like they tell you not to do it. And the reason is because when electrical workers come work on the lines, they can get shocked, because if you don't turn this off, they tell you to turn this off. If you don't turn this off, then the electricity that you're charging in your house will actually go back up out into the power lines, and you can hurt somebody. Ever done that? I haven't. Okay, good. Oh, nice. But don't do that. But if you do it, make sure that you turn off the main breaker handle, because that separates you from the grid outside in the wide world. Okay, circuit breaker sort of works like this. This will make more sense to you later. Actually, there are 2 types of circuit breakers. This is an older one, which is sort of similar to the old thermostats. You know, seen the old thermostats? They're round. If you pull them off, there's a coil inside of them. Okay, well, this is sort of similar to that. where you have current that comes in, it goes through this bimetallic strip, and then goes around and goes out the other way. But when current goes through that bimetallic strip, it heats it up, and depending on the temperature of that strip, it can bend one direction or the other. We talked about this last semester, about how when you heat a metal, it expands. So when you have this bimetallic strip, I heat one side or the other, and it can make the bimetallic strip bend one way or the other, depending upon which metal expands the most. So like if this side expands more than this side when I heat it up, it's going to bend in this direction, because this side will get longer, or vice versa if you go in this direction. And so that's what this does, is this bimetallic strip will bend one direction or the other. These days, mostly you have these electromagnetic switches. You'll see this in the next chapter, in chapter 5. We'll talk about solenoid switches. A solenoid switch, you have a current that goes around a magnet, and it interacts with the magnet because a current creates a magnetic field. It'll interact with the magnet to open or close the switch. Don't sweat that too much right now, but just know that these switches operate through a magnetic field. So you can either have thermal or you can have magnetic switches in these circuit breakers. Okay, let's try this. I want you to calculate, and if you ever design your house, like what you want on a circuit, you'll need to design, sort of think about what are the devices that you have on that circuit, and what can the circuit safely handle. So in this case, you have a 1200 watt heater and these other things, but then you turn on your television and it flips the circuit breaker. So I want you to tell me what is the maximum allowed current for this breaker, for this circuit breaker. All right, just a few more seconds. We'll stop at say 210. I'll hand back your exams. 210. Okay, so very good. C is right. What you want to do here is figure out the current that goes for each device. So power is equal to V times I. So if I want to figure out the current that a device carries, you say P over V. So for example, for the 1200 watt heater, that's 1200 watts over 120 volts. That's equal to, what's that, 10 amps. So the heater, it pulls a lot of current. When you have a heater, like a bathroom heater, that's usually your culprit that's going to sort of tip the limit on your circuit breaker because it carries so much current. Now we can do the same for these others. This is 1 amp, 120 over 120. This is 1 amp. So at this point, I have 10 plus 1 plus 1 equals to 12 amps. And then I add another 4 amps. So I'm going from 12 to 16 when I add that TV. That means that the circuit breaker is somewhere between 12 and 16. And so C is the right answer. That's the only number that's greater than 12 but less than 16. All right. You know where a bad light ends up? In a prism. Okay, I'm going to hand back your test now. Let me stop this. We'll wrap up there. We'll finish up this chapter next time.